Probably the most influential speaker of this weekend is Dr. Gerald Niznick. Don't need to introduce him much because his DNA runs through our implants. Just about every implant out there in some capacity, form or another, has something that comes out of Dr. Niznick. If you're in the space of designing implants, testing implants, setting up companies, it's almost impossible not to know who this gentleman is. With 33 US patents, he is easily considered as one of the biggest, greatest minds and innovators of our time, not just in the profession of implantology. He's going to be addressing you because he was there from the very beginning as this industry shaped and took its shape over the last few decades.
Thank you for the invitation to be here. And in 1 hour, I'm going to go through the evolution of implants, but I'm also going to spend quite a bit of time on all the controversies that exist and hopefully give you a roadmap for the future of implants.
Here are the implant systems available in 1979 when I started to develop the Corvent system. The basket of the Straumann hollow basket implant was the genesis for the Corvent design, but Straumann's implant left a big gap at the crest after you drilled the hole. Corvent solved that problem. The German IMZ implant with its intermobile element, osseointegrated, but was a prosthetic nightmare. Subperiosteal implants, blades, pins, and ramus frame implants were popular in the US in the 1970s, but with unpredictable results. The French Scortecci disc implant and the staple implant used by oral surgeons all were obsoleted by the Corvent and Brånemark screw implants. I launched the Corvent hollow basket implant in 1982 with a hex hole in the top that accepted a variety of application-specific cemented abutments. This journal advertisement from 1983 shows cases of various clinical applications with the Corvent, and this 1984 brochure shows some of the same cases. Here is the Corvent patent, the Corvent attachment patent, and a patent on a castable abutment. This picture of me was from 1986. What the Corvent system pioneered was application-specific abutments. It really created the field of implant prosthodontics. Corvent initially offered a wide variety of cemented abutments for screw-retained bars, overdenture attachments, ball attachments, magnet attachments, and both straight and angled abutments for cemented crowns and bridges. In 1986, I developed the screw vent with a lead-in bevel internal hex connection. The original screw vent connection with its 45-degree lead-in bevel is the most widely used connection in the world today. Many companies offer implants with 74 to 84-degree lead-in bevels. The lead-in bevel, regardless of its angle, provides lateral stability that contributes to fixation screw stability and allows for the design of narrow implants. Since all conical connections, whether 45 degrees or 84 degrees, primarily only make contact at the opening of the internal socket, all the longer bevels do is thin the walls of the implant. The screw vent patent expired in 2007, 17 years after it was issued and 20 years after the patent was filed. Here is a 31-year-old follow-up x-ray of a case I did in 1986 using a Corvent and the very first screw vent ever placed. It was on my mother-in-law and remained in perfect condition for 32 years when she passed away in 2018 at the age of 99. The Corvent surgical protocol was to place the implant 1 millimeter above the crest to facilitate uncovering. The use of a wide 5.3 millimeter diameter implant, in this case, further contributed to what appears to be bone loss to the first thread. This slide shows a 1985 article in the LA Times talking about the Bronnemark system and my core vent system. After I launched the screw vent in 1986, I developed the first comparative advertisement in dentistry. This ad appeared in the Journal of Oral and Maxillofacial Surgery and acknowledges that there is a difference between the screw vent and the BLX implant, which was what the Swedish Bronnemark implant was then called. It points out that one of the differences is the price. For $20,000, a dentist could buy 25 Bronnemark implants and surgical instruments. But for the same amount, a dentist could buy the screw vent system, including the same number of implants and instruments, and have enough left over to buy a Volvo and take a trip to Sweden. At that time, the screw vent differed primarily in its abutment connection from the Bronnemark implant, which had an external hex connection. This slide shows some additional patents I was issued in 1988 and 1989. I developed the BioVent cylinder and the MicroVent, which was the first small diameter implant, and had ledges and apical threads for a push-in, screw-in surgical protocol. Also shown here are patents of my early attempts to create angled screw-in abutments. CoreVent was the leader in education throughout the 1980s, live surgical courses in my office and lectures all over the country. CoreVent held the first symposium by an implant manufacturer in 1987 in Chicago with 650 attendees. It was repeated in 1988 in Dallas with over 800 people attending. In 1988, Gordon Christensen did an independent study of the CoreVent system and pointed out its many advantages. CoreVent received ADA provisional approval in 1989. That year, I introduced the SweetVent external hex implant, which was a clone of the Bronnemark implant. By 1990, the ScrewVent's internal hex connection completely replaced the hex hole connection for the cemented abutments on the CoreVent, ScrewVent, and MicroVent implants. In 1990, I patented fixture mount packaging, where the implant was provided suspended on a carrier that could be used as a transfer. This was also the industry's first sterile packaging. The Spectra system concept proposed the use of different implant designs and materials for different qualities of bone. From 1990 through 1995, I funded a study using 2,795 Spectra system implants in 32 VA centers and universities. It was an independent, prospective, randomized, double-blind, double peer-reviewed study under the control of a team from the Veterans Administration. The results and study protocol were published in a special issue of the Journal of Oral and Maxillofacial Surgery, and the 3 to 5 year results were published in a special issue of the Journal of Periodontology. This 3-year follow-up article in the JOMS reported on the results of HA-coated implants used in the study compared to the acid-etched, non-coated implants. The study compares the Spectra system's different implant designs, materials, and surfaces in different qualities of bone found at different locations in the mouth. What we learned was that HA coating enhances success regardless of the bone quality, the surgeon's experience, antibiotic therapy, or whether the patients were smokers. HA-coated implants were 98% successful across the board. The HA-coated implants held up very nicely over the 3-year period, whereas the success with the acid-etched screw vents started to drop off. Etching with hydrofluoric acid, which was the way we were treating the machine surface of the non-coated implants to assure a clean surface, made the surface relatively smooth. So right after that study, I switched the etched surface implants to what's called SBM, soluble blast media, creating a texture on the surface by blasting with water-soluble HA crystals. The CoreVent in the early 1980s was blasted with aluminous oxide and then had to be acid etched to get those particles off. From 1991 to 1997, Dentsply became the exclusive distributor of the Corvent products. Dentsply's advertisement, shown here with a C passing through a D, claims that now the biggest name in implants joins the biggest name in dentistry. In 1990, Corvent was the biggest implant company in the world, selling more units than Nobel. Shown here is Corvent Bioengineering that I built in 1994 for the manufacture of the Corvent product line using 36 CNC machines. In 1992, I was issued a patent on a transfer with one flat side to allow positioning of the implant analog's hex in the same rotational position as the implant's hex in the mouth. Before the introduction by Corvent of two-piece straight and angled abutments for cemented restorations, there was no need for such transfers. That patent also included claims on what is called a friction fit connection, a flagship product feature of Zimmer Biomet today for the screw vent implant system it bought from me in 2001. By tapering the male hex 1 degree and making it slightly larger than the hex hole of the implant, it required 30 Newton centimeters of torque just to seat the abutment in the implant. The abutment could only be separated from the implant by threading a tool through the internal threads of the abutment. As the tool continued to turn, it bottomed out inside the implant and jacked the abutment out of the connection. In 1994, I patented healing collar packaging with a friction fit healing collar that was used as an insertion tool, remained in place as the healing collar, and then could be used as the transmucosal portion of a two-piece abutment. Different screws were inserted to achieve the desired prosthetic result. Retaining the healing collar in place and converting it to be part of the abutment avoided disturbing the soft tissue attachment after healing. Both the healing collar abutment and the prosthetic screw fit into conical connections for optimum stability. In 2017, Nobel introduced what it called the On-One concept. The On-One healing collar is attached to the implant with a fixation screw, which itself is designed to receive a fixation screw attached to the top to retain the abutment. My 1994 design required only one screw with different designed prosthetic heads passing through the friction fit healing collar to engage the implant's internal threads. The Nobel One healing collar is designed to fit into the conical connection of the Nobel active implant, but the top of the On-One healing collar provides a butt joint connection for the abutment attachment, which, like the two-piece screw system, could compromise stability. In 1997, I terminated the Dentsply contract and renamed the company Paragon. In 1999, I launched the tapered screw vent with triple lead threads, both with fixture mount packaging and with friction fit healing collar packaging. As seen from this cross section, the friction fit actually forms a cold weld between the parts. In 1995, I filed a method patent on inserting a tapered implant into a straight socket, generating high initial stability. In 2000, I wrote an article on the surgical protocol demonstrating that in soft bone, placing a tapered implant into an undersized socket would generate higher initial torque. If the bone was dense, the socket is enlarged using a diameter drill only slightly smaller than the implant diameter. And if the bone is very dense, the use of a cortical drill that opened the top of the socket to match the implant's diameter could be used. Using this soft bone, hard bone surgical protocol, there is no need for bone taps. Here is an article published by Shalaby that shows that placing an implant into an undersized socket has a decisive effect on implant fixation, represented in the study by installation torque values, removal torque, and histomorphometric evaluation of trabecular bone. So in other words, if you put bone under compression, you're going to have not only higher initial stability, you're going to have higher bone contact. That was the whole basis of the tapered screw vent and its soft bone, hard bone surgical protocol. In 2001, I sold Paragon to Calcitech. It was subsequently renamed Center Pulse before it was acquired by Zimmer Orthopedics and renamed Zimmer Dental. Zimmer Orthopedics ultimately acquired Biomet, which owned Implant Innovations, known as 3i, and it's now called Zimmer Biomet. The tapered screw vent is still their flagship product with its friction fit abutment connection. Zimmer Dental published 10-year results with the tapered screw vent showing very high success. In 2004, 3 years after selling Paragon to what became Zimmer Dental, I founded Implant Direct in the Corvent Bioengineering factory. Implant Direct launched the Spectra system and RePlant system in October 2006 at $150 per implant. What this did was create the value segment of the implant industry by providing cross-compatibility with Zimmer Dental's screw vent and Nobel's replace implants at substantial cost savings. This was made possible by the cost savings of online ordering and the added value of all-in-one packaging. Implant Direct was featured in an article entitled Shop of the Future because of the efficient lights-out manufacturing that allowed 24/7 machining of components without anyone in the building at night. Implant Direct's online ordering and customer service received the highest rating of customer satisfaction in one independent survey. Eventually, Implant Direct expanded with a national and international sales force. Here are some of the other patents I was issued. One for a two-piece healing collar with a screw that also seats on the implant, one for microthreads, and another for a fixture mount that could be used as a transfer or shortened for use as a straight snappy abutment. The Spectra system included 6 implants, all with the same body, but with different application-specific platforms. If the dentist knew the desired prosthetic outcome of the case, the proper selection of a Spectra system implant would provide the abutment, transfer, and healing collar in the implant vial. This simplified ordering and provided substantial cost savings. Here is a case with the ScrewPlant implant, which is like the screw vent but with an external bevel. The all-in-one packaging includes the fixture mount that can be shortened to a snappy abutment. Snap-on comfort caps are also provided. In this case, all 10 implants osseointegrated. This slide shows the use of the ScrewPlant's snap-on transfers that come with the implant. The final restorations for this patient are 2 full-arch cemented bridges. 2 of the one-piece implants included in the Spectra system are the Go Direct for overdentures and the Screw Indirect for screw-retained hybrid bridges. The Go Direct with a Zest locator compatible platform is also internally threaded so that it can be converted to a multi-unit abutment. If the tissue overgrows the top of the implant, you can add a 2mm extender abutment. The case on the left shows 4 Go Direct implants in the symphysis, and the case on the right shows 4 Screw Indirect implants in the symphysis. This slide shows the Go Direct one-piece implant with a locator compatible platform and all-in-one packaging. The packaging included what I called the GPS attachment. I received a patent on the GPS and it offered several advantages compared to the Zest locator attachment, some of which have since been incorporated into the newer Zest attachments. After Danaher bought Nobel, they eliminated the GPS from the market and started selling the Zest locator instead, which is unfortunate. Here is a case of 4 Go Direct implants placed with a flapless surgical protocol. Because Go Direct is a one-piece implant, it can be made in a 3mm diameter and still retain adequate strength. Here is a screw indirect implant with its all-in-one packaging. The screw receiving multi-unit platform of the implant has a retentive groove for a snap-on transfer and snap-on comfort cap that are included in the package. The package even includes a 2mm extender abutment in case of tissue thickness. The platform is designed to accommodate 40 degrees of divergence while still being able to seat the framework. This will allow distal tipping of the implants up to 20 degrees, eliminating the need to buy expensive angled abutments. Here is a case showing reflection of the flap and placement of 4 screw indirect implants. This slide shows the snap-on comfort caps and transfers provided with the screw indirect implant and the soft tissue health around the necks of these one-piece implants. The final prosthesis was a bar overdenture, but it could have been a screw-retained hybrid bridge on the same implants. This case, done by Dr. Ed Mills, shows the placement of 5 3mm diameter screw indirect implants placed in the symphysis after the thin crestal bone was removed. I strongly recommend laying a flap if you have a very thin ridge so you can recontour the bone as shown here. After bone grafting in the edentulous maxilla, Dr. Mills placed 6 screw indirect implants. This shows the beautiful soft tissue healing before and after the removal of the snap-on comfort caps. Dr. Mills chose to use screw-retained open tray transfers rather than the snap-on transfers provided free with each implant. I agree with Dr. Mills that if there is available bone for 5 to 6 implants in either edentulous arch, why only put in 4 implants and risk delaying treatment or having to remake the prosthesis if one of the 4 implants fails to osseointegrate or loses integration in function. The cost of the implant isn't that expensive compared to the cost of remaking the bridge, so why not put in an insurance implant or 2? In 2007, Implant Direct launched the RePlant Legacy and Swish industry-compatible implants, including a broad line of Nobel Replace, Zimmer screw vent, and Straumann compatible abutments. I received a patent on the only way around the Nobel Replace trilobe implant, which allowed Implant Direct to take a big bite out of Nobel's business. The RePlant trilobe implant offers surgical and prosthetic compatibility with the Nobel Replace implant. The RePlus and Reactive trilobe implants were designed with a tapered body like the Spectre system implants with multifunctional fixture mounts. All 3 offer improvements over the Nobel Replace, such as microthreads, a self-tapping cutting groove, and use of stronger titanium alloy. These cost-effective alternatives to the Nobel Replace implant have been relegated to relative obscurity after Danaher acquired Nobel Biocare and merged it with Implant Direct under Nobel's management. When the screw vent patent expired in 2007, Implant Direct introduced the legacy implant system that evolved from 1 implant to 4 by 2013. Legacy 2, 3, and 4 have more aggressive threads than the Legacy 1 implant and differ primarily in the design of the implant carrier. This 5-year prospective study using Legacy 3 implants by Dr. Cavallero of Columbia University documented 100% success. The study reported only 0.6 millimeters of bone loss on the average over the 5-year period. The Legacy 2, 3, and 4 implants offer 7 diameters and 6 lengths, making it the most versatile system in the industry. Widths range from 3.2 millimeters to 7 millimeters, and lengths range from 6 millimeters to 16 millimeters. Unlike many systems claiming simplicity by offering only one platform connection, regardless of the implant diameter, the legacy system includes 4 platform diameters to assure ideal emergence profile regardless of the diameter of the implant selected. On the left is the cover of a legacy catalog showing the 4 legacy implant options, and in the center is the profile of the legacy 2 and 4 with the top 1/3 straight and the bottom 2/3 tapered. The cutting grooves extend up to the straight portion for efficient self-tapping. All of the legacy implants have double lead threads merging with quadruple lead microthreads. On the right, we see the Legacy 4's patented 3-piece carrier with a snap-on square on the top to provide the accuracy of an open tray transfer with the simplicity of a closed tray transfer. This slide shows the 7 diameters and 4 platforms of the Legacy 4 implant and the all-in-one packaging that includes the 3-piece carrier that is a straight abutment and a transfer. A 2 millimeter healing collar and cover screw are also included. This shows the use of the patented 3-piece abutment transfer. When you make the impression, the top part of the carrier will be incorporated into the impression. You can then attach the abutment to an implant analog and insert it into the impression. You'll hear a snap as the 2 metal parts mate. This will give the accuracy of an open tray transfer with the simplicity of a closed tray transfer. Alternately, you can leave the abutment in the mouth to support a temporary crown and use an abutment analog to snap into the metal part embedded in the impression before pouring up the working cast in stone. The same type of 3-piece carrier is provided on the interactive implant, which differs from the Legacy 4 implant only in that it has a Nobel active compatible internal conical connection rather than the screw vent's internal conical connection. This case by Dr. August de Oliveira shows the flapless placement of a Legacy 4 implant into a previously grafted socket. This shows the Legacy 4 abutment with its concave neck. For some reason, August tried to use a regular healing collar, but since he had put the implant slightly below the crest of the ridge, it didn't fully seat. He changed back to the 2 millimeter healing collar provided free with the implant. Longer healing collars are available with similar contoured necks. After a non-submerged healing period, a scan post was attached and the final restoration fabricated. August also did my implant, an immediate placement and temporization of the maxillary right central. This is the holy grail of implants, to be able to immediately replace a tooth with an implant and send the patient off with a temporary crown. That's what I've been working for 40 years. Several decades following endodontic therapy and a post and core on my tooth, the root fractured and the tooth had to be removed. August took the tooth out and made a surgical guide using his Cerec machine. He started the surgery using the guide. I wanted to change the angle just a bit, so I guided his handpiece while looking in the mirror. You might call that Niznick guided surgery. I requested that he use an HA-coated Legacy 4 implant. Now that a 5-year study documented 100% success with SBM blasted Legacy implants, the same surface Zimmer and BioHorizons are using, why did I choose to use an HA-coated implant? I will show you studies that prove HA really gives a stronger attachment to bone. I wanted to make sure everything was working in my favor. You will note that the HA starts several millimeters from the top of the implant, although the VA study did not show any soft tissue differences between implants having HA to the top and those with acid-etched smooth surfaces. This shows removal of the free titanium abutment that comes with the implant and replacement with Implant Direct's abutment having zirconia cemented over a gold anodized titanium base. This surgical picture shows bone loss of the labial plate caused by infection. This was caused because I delayed by 2 weeks removing the fractured tooth. August just grafted it, protected the graft with a membrane, attached the zirconia abutment, and cemented a temporary crown. This shows healing after 2 months. The zirconia abutment with a 1 millimeter collar was replaced with one having a 2 millimeter collar so that the margin of the restoration would not have to be so far subgingival. The final abutment was torqued in to 30 Newton centimeters and the temporary crown was replaced. Dr. Guillermo Roman, a prosthodontist, prepared my other central and the zirconia abutment. After making the impressions, temporary crowns were fabricated and cemented. This shows the final results taken shortly after the crowns were cemented. It has been 4 years since this case was completed with no problems at all. It feels like my own tooth. In December 2013, Implant Direct launched the interactive implant with a 78-degree lead-in bevel internal hex connection, matching that of the Nobel Active implant. This was primarily just to go after the Nobel Active implant and abutment business. The body of the interactive implant is the same as the Legacy 2 and 4 implants, with the addition of micro grooves added above the micro threads. After Danaher acquired 100% of both companies and Nobel took over the management of Implant Direct, you don't hear too much about the many advantages of the interactive implant because of its substantial cost savings compared to similar components of the Nobel Active system. This is an article that was written on the interactive implant. The rationale for adding micro grooves above the micro threads, which was the basis for receiving the patent, is that horizontal grooves and threads both retard bone loss, but if either were to become exposed to the soft tissue, the hygiene and soft tissue attachment to micro grooves would be more easily maintained. There are a number of design advantages when comparing the interactive to the Nobel Active. The interactive does not have a back tapered neck that can create a gap at the crest of the ridge. Its micro threads add to stability compared to just micro grooves with the Nobel Active. The interactive self-tapping cutting grooves extend up to the straight part of the implant and function to cut bone when the implant is rotated clockwise into the socket. Nobel's cutting groove, on the other hand, only functions when the implant is rotated counterclockwise. This design was incorporated to help unscrew the implant when its very steep 9-degree taper results in the implant getting stuck in dense bone during insertion. The interactive implant, by contrast, has only a 2 to 3 degree taper and can be inserted self-tapping in all qualities of bone. Another feature of the interactive is its round apex in contrast to Nobel Active's flat, sharp apex, which can allow the implant to change its trajectory during insertion and possibly damage the sinus membrane if the floor of the sinus is perforated. Since 1984, when I wrote an open letter to oral surgeons in response to a letter sent them by Nobel Biocare, I have been addressing the controversies and the misinformation related to dental implants that has been generated to promote the sale of dental implants. Here are 3 examples: a controversies brochure on implant connections and surfaces, an open letter to Nobel customers, and an analysis of Zimmer Dental's trabecular metal surface applied to the tapered screw vent implant. This January 2018 Clinical Research Associates survey of 1,120 dentists using value-priced implant systems from 10 companies showed that 54% of the dentists were using Implant Direct systems. Implant Direct was the dominant player in North America value segment of the dental market. These are some of the articles and journals I wrote while I was president of Implant Direct. I sold 75% of the company to Danaher's Cybron division at the end of 2010 and remained president of the joint venture through 2013, and then sold my remaining 25% interest in January 2014. Danaher acquired Nobel Biocare the end of 2014, and today Implant Direct is managed by Nobel Biocare's executives, so it can control the effectiveness of what was once its most aggressive competitor. In the next 44 slides, I will address many of the questions and controversies related to dental implant products and procedures. A common question is, what is the best design for the body of the implant? This slide shows wide variations available with different thread patterns, tapers, and designs of cutting grooves. Straumann recently introduced the BLX implant, designed by the same dentist that created the Nobel Active implant. The Nobel replaced trilobe implant without a cutting groove is basically the same design as it was when Nobel bought Stereos in the late 1990s. Implant Direct's RePlant trilobe implant is surgically and prosthetically compatible with the Nobel Replace implant, but with microthreads and a vertical cutting groove added. The Nobel Active has a back tapered neck, deep threads, and a 9-degree tapered body. The Legacy and Interactive implants, on the other hand, have a 2 to 3 degree tapered body with efficient long cutting grooves and a round apex. Another question is, what constitutes an effective self-tapping design for a tapered implant? Straumann's Bone Tap, similar to those of other companies, is designed with a flattened relief area that advances ahead of the vertical cutting groove as the implant rotates clockwise into the socket. The Legacy 2 and 4 implants have a long cutting groove extending up to the major diameter of the implant with a relief area similar to a bone tap. This is in contrast to the Nobel Active, with its relief area trailing the cutting edge, so it's only effective for unscrewing the implant. The BLX implant has very deep threads that are wider than the top of the implant, and while its core is tapered, it is basically a straight implant. It has grooves cut through the threads at an angle, but without any relief area traditionally found in bone taps. Many companies contributed to the evolution of implant design, starting with the Straumann basket implant with its narrow neck of the 1970s. This led to the development of Corvent's hollow basket screw implant in 1982. By 1985, Straumann added threads and a full diameter neck to its hollow basket implant, but ended up violating the Corvent patent. After a court battle, they had to take it off the market for 6 months until we reached a licensing agreement. In 1990, Straumann switched to this straight cylinder screw that proved that a one-stage surgical protocol was as successful as burying the implant during the healing process. It took Straumann until 2007 before it introduced a bone-level implant. Here we see the new Straumann BLX bone-level implant with very deep threads that extend beyond the diameter of the neck of the implant. This is similar to the MegaGen Korean implant. My first rule of implant design is that the widest part of the implant should be at the crest of the ridge to seal it. Wider threads can expand the opening to the socket as the implant is inserted into the bone, leaving a gap between the neck of the implant and the bone. This case shows the BLX implants inserted into the bone grafts following sinus elevation. The mesial implant is shown stopping 2 millimeters from full seating before inserting the distal implant to allow verification that they are relatively parallel. After the mesial implant is fully seated in the graft site, the narrow neck, having passed through the widened crest of the ridge, loses stability and is no longer parallel to the distal one. The image in the center shows, by contrast, a 10 millimeter legacy implant and bone grafting material elevating the sinus membrane. Its design with microthreads may be essential for achieving initial stability with only about 5 to 6 millimeters of the implant surface engaging the porous maxillary bone. Here is a case with 16 Legacy 3 implants done by Dr. Gary O'Brien. He states that, quote, "I just uncovered a case with 16 Legacy 3 implants and there was 0 bone loss on all 16. Very impressive surgical results. This is by far the most user-friendly, forgiving, bone-loving implant design I've ever placed," end of quote. I don't see any purpose in designing a cylindrical screw implant with a back taper to the neck like the Nobel Active, having threads wider than the neck like the BLX, or turning the cylindrical neck into a triangle like MIS's V3 implant, which I will discuss further in later slides. MIS's V3 implant turns the cylindrical neck into a triangle, claiming that this will help preserve a thin labial plate of bone. When the round drill cuts a hole that thins the labial plate, the damage has already been done. Having a blood clot between the bone and the flat surface of the triangular implant is not going to reverse that damage. A better solution is to use a narrower implant that does not require thinning the labial plate, or drill a smaller hole and expand the bone by the self-tapping insertion of a tapered implant. MIS cannot put the triangular shape on a small diameter implant because there's not enough metal. MIS's rationale for using its V3 implant fails in an immediate extraction socket as shown here, where a wider diameter cylindrical implant would have reduced the need for bone grafting material and allowed for a better emergence profile for the abutment and restoration. MIS also includes a final sizing tapered drill with each implant, but with a tapered implant being inserted into soft bone, the final sizing of the socket is completed with an intermediate drill. Another question is whether deeper threads increase stability in soft bone. Here is a marketing piece from Zimmer Dental that compared the initial torque of its tapered screw vent implant to that achieved with the Nobel Active, Nobel Replace, and Straumann straight bone level implant. The screw vent generated 100% more primary stability than the Straumann straight bone level implant and 29% more than the Nobel Active, with much deeper threads. The deeper the threads, the wider apart they need to be, and this creates more space for the soft bone to push in as the implant is inserted. With shallower threads, the inner core of the threads compress the soft bone as the implant is inserted, self-tapping, generating higher initial torque and greater stability. I am no fan of the use of osseodensification drills that run backwards, supposedly compressing the bone as it pushes it laterally. Osseodensification occurs naturally by inserting a tapered implant self-tapping into an undersized socket, and the compacted bone is between the threads where it can do the most good in increasing stability. Is the cost of the implant directly related to clinical success? The answer is no. Here's a case where 2 Legacy 4 implants were used adjacent to a Straumann bone level implant. The U.S. list price for the Straumann components for the implant and abutment was $838 compared to only $230 for each all-in-one package Legacy 4 implant, which includes the transfer, abutment, and healing collar. Straumann introduced a bone-level implant in 2007, and it took them until 2014 to offer it tapered. Now Straumann launched a zirconia implant for $595. I don't know what problem it solves, but I certainly can see what problems it could cause. You can't change the angle, you can't change the margin, and you can't use it for immediate load because you can't use more than 20 Newton centimeters of torque during insertion, according to a UCLA speaker I recently heard. So let's talk about the question of all on 4, 3, or 2 implants and whether to place the distal implants straight or at an angle to reduce the length of the cantilever extension. This is a Nobel all-on-4 case in the upper and lower edentulous arches with what looks like straight Nobel Speedy implants. Angling the distal implant requires the purchase of $250 angled abutments. This x-ray shows a case Nobel posted on Facebook or LinkedIn. If you take a close look at the distal implant, a radiolucency around the entire implant is evident. The bridge is holding the implant in rather than the other way around. That implant should be removed, and that would necessitate shortening of the bar, which is why it is prudent to place 5 to 6 implants in the edentulous jaw if bone is available, to avoid having to remake the prosthesis if one of the implants fails, as occurred here. Nobel has now launched its trefoil system using just 3 straight implants in the symphysis. This basically steps on their own message of all on 4 with distal angled implants. There's a school of thought in Europe where they're putting in just 2 implants, as shown here. This zygomatic implant case was done by Dr. Ramzi Amin. If he can justify a long cantilever from engagement with only a small amount of bone in the zygoma, why do we need angled distal implants in a lower case to shorten the cantilever? Just put 5 implants straight up and down, as I show here graphically, and if you were able to do that, why not use one-piece implants like the Sere Indirect and save the cost and time of attaching the abutment? This is a case posted on Nobel's website using all-on-4, showing in the maxilla with what they refer to as the optimum implant distribution. Look at all this bone behind the distal implants. Graphically, I showed that there was available bone to place 6 straight implants. In my opinion, that would optimize implant distribution, building in redundancy and eliminating the need for angled abutments. The interactive implant was developed as a cost-effective alternative to the Nobel Active with many design improvements. For example, the Nobel Active has a back-tapered neck with micro grooves, while the Interactive has a straight neck to seal the crest on insertion and adds micro threads for added stability. The Nobel Active is tapered 9 degrees with cutting grooves designed to function in counterclockwise rotation to assist unscrewing of the implant when its aggressive taper results in it being wedged into dense bone. The Interactive has only a 2-degree taper, and its self-tapping grooves facilitate insertion in both dense and soft bone. This slide shows the bone loss associated with the back-tapered neck of the Nobel Active implant. My preference is to have a straight neck to the implant in order to seal the opening of the implant socket at the crest. This SEM of an HA-coated screw implant shows the transition from the SPM blasted microthreads to the HA-coated threads of the body. The surfaces look almost the same. This case shows an internal sinus elevation with only about 4 millimeters of bone below the sinus floor. Having threads engage this limited height of bone will determine whether there is adequate initial stability for the implant to osseointegrate. This is where a micro-threaded neck may be essential for implant success. Back tapering the neck, as with the Nobel Active, or minimizing bone contact with a triangular-shaped neck, such as the V3 implant, is not beneficial. The disadvantages of a sharp apex versus a round one is the increased risk of tearing the sinus membrane if the floor of the sinus is perforated. A sharp apex can unintentionally result in changing the trajectory of the implant during insertion in soft bone from that determined by the drilling procedures. A number of implant systems only offer one diameter to the abutment connection for all diameters of implants, claiming the advantage of reduced abutment inventory. The Neodent, Straumann's Brazilian value-priced implant, has 5 diameter implants with just 1 diameter of internal shaft. In the case of Neodent, with its long lead-in taper, this requires long abutments and usually requires countersinking of the implant during insertion. These abutments with the Neodent wide implant create an undesirable emergence profile. This is in contrast to the legacy system's 7 implant diameters with 4 different abutment connection diameters to facilitate the optimum emergence profile. Straumann's new BLX system also offers 7 implant diameter options, but all with the same diameter abutment connection as shown here. Straumann recognizes the need for wider emergence profile abutments and offers them for the 5, 5.5, and 6.5 millimeter diameter implants, but these abutments sit on the top of the implant, abandoning the advantage of the implant's internal conical connection. Debate exists over whether the top part of the implant should be textured or smooth. Implant Direct, after I retired as president, launched the Legacy P implant with a smooth neck. But if you already have 100% success with SBM extended to the top of the implant and a documented bone loss of only 0.64 millimeters after 5 years, why look for something different? We know that bone tends to run down a smooth surface. As shown here, Nobel offers all different kinds of variations to the necks of its implants. With the Legacy implant having a very high documented success rate with very little bone loss, I firmly believe in extending its SBM textured surface to the top of the implant. This is a case done with the Legacy P implant launched after I retired and against my advice. In 1994, I developed what was called selective surface with a smooth surface on the top, smooth on the bottom for more efficient self-tapping, and SBM blasted surface in the middle. I've looked at all of these combinations and went with light blasted SBM surface over the entire length of the implant. Blasting with aluminous oxide like Straumann and titanium oxide like Astra requires a final wash with acid to remove the embedded particles. With SBM, which is water-soluble HA crystals, this additional procedure, which tends to round the threads and cutting grooves, is not necessary. Here is a study by Dr. Danny Boozer comparing Straumann's tissue-level implants blasted all the way to the top, with the same implants having the top 2 millimeters smooth. As reported in this study, quote, in general, implants placed with the top of the SLA surface above the bone crest had significantly less bone loss than implants with the top of the SLA textured surface level with the bone, end of quote. This indicates that a textured surface in the soft tissue does not contribute to bone loss. What is the best implant abutment connection? The internal connection with a lead-in bevel, first introduced in 1986 with the screw-vent implant, is the cornerstone of modern implant design. Clearly, internal conical connections won out over external hex connections and over internal connections with butt joints like the Nobel replaced trilobe implant. Nobel now offers the replace with a conical internal hex connection. This external hex southern implant shows wear on the interface and the company recommended 45 Newton centimeters of torque on the fixation screw to bolt the abutment to the implant, whereas most internal connection systems recommend only 30 Newton centimeters. Astra Implants, with an 80-degree lead-in bevel that creates thin walls, recommends using only 20 Newton centimeters. The Nobel Active and Implant Direct's interactive implants have a 78-degree lead-in bevel in contrast to the 45-degree lead-in bevel of the original screw vent connection replicated in Implant Direct's legacy implant system. When you have a long, steep bevel, the walls get thinner and the hex gets deeper. When the Nobel Active was first launched in 2008, shortly after my internal conical connection patent expired, the company recommended that X-rays be taken to confirm that the abutment was fully seated. Straumann recently introduced the BLX implant with an 84-degree lead-in bevel, but they had the good sense to keep it relatively short. It is generally accepted that internal conical connections with lead-in bevels are the preferred design because of the stability between mating parts. All of the abutments for implants with lead-in bevels should be made with a half-degree less taper to ensure contact at the opening of the internal shaft. This graphic of a pal-top connection demonstrates this fact. Therefore, having a steeper or longer taper to the implant's bevel does not contribute to greater stability. This picture of a cross-section of a Neodent Grand Morris implant with its 74-degree taper demonstrates what happens if the first point of contact is down the bevel and not at the opening of the internal shaft of the implant. A gap is created at the opening of the shaft. A Morris taper is 1 to 1.5 degrees, not 16 degrees as used by the Neodent implant. This slide shows a case using the Astra implant, which has a long 80-degree internal bevel. Tightening the fixation screw to seat the long bevel of the abutment results in lateral forces on the thin walls of the implant, which is why this company only recommends 15 to 25 Newton centimeters of torque for tightening fixation screws, depending on the diameter of the implant. As shown here in these follow-up x-rays, the lateral forces on the thin walls of the implant resulted in part of the implant's wall fracturing. This resulted in a loosening of the abutment and significant bone loss, with the ultimate removal of the implant. What is the best implant surface has been a question for debate since the early 1980s. With Nobel selling smooth machined surface implants, Straumann selling rough, porous titanium plasma sprayed surface implants, and Corvent selling implants with a textured surface created by luminous oxide blasting followed by hydrofluoric acid etching. By 1991, Corvent started blasting its implants with hydroxylapatite crystals, creating a medium rough surface without the necessity to acid etch to remove particles. The machined surface Nobel implants proved to be too smooth for good success in soft bone. In about 2004, Nobel introduced Tyounite, a rough, porous surface created by anodizing. Straumann abandoned its rough, porous TPS surface in the late 1990s, replacing it with large grit luminous oxide blasted surface followed by acid etching, which was referred to as SLA. Straumann subsequently introduced a premium-priced version of this surface called SL Active. This consisted of packaging the SLA surfaced implants in sterile saline to isolate it from carbon deposits from the atmosphere until the time of insertion. Straumann claimed this improved bone attachment by making the surface more hydrophilic. Implant Innovations promoted its OsseoTite acid-etched surface, which was even smoother than the machine surface. Calcitech in the late 1980s promoted a low crystalline HA-coated surface coated to the top of their cylindrical implant. That was essentially replaced with a high crystalline HA surface. All of these early blasted surfaces of Straumann, Corvent, and Astra have stood the test of time, as have the HA-coated surfaces. Nobel just modified its TiUnite implants by anodizing the top few millimeters of the implant, creating a very smooth surface to minimize complications from exposed TiUnite. Nobel posted on its website this meta-analysis of studies reporting favorably on its TiUnite surface by Dr. Albrechtsen, one of its paid non-dental opinion leaders. The results of 106 studies, according to Albrechtsen, showed only 5% of the patients had peri-implantitis. I always questioned Albrechtsen's veracity after I uncovered in the late 1980s that he and Branemark, in a 1983 article, had misrepresented as an osteoblast an SEM of a fibroblast that had appeared in a 1982 article. That same phony picture later appeared colorized on the cover of Branemark's textbook. If the TiUnite rough porous surface does not contribute to soft tissue complications and subsequent bone loss, then one might ask why Nobel is now replacing TiUnite on the top few millimeters of its implants with a smoother anodized surface. Here is a copy of an email sent by a periodontist in Toronto to some Nobel sales representatives, and for some reason he copied me on it. He is telling these Nobel reps that at least 25% of his cases with Nobel replaced TiUnite implants are showing, quote, an unacceptably high degree of early bone loss, end of quote. So where does the truth lie? I think you want to have a medium rough textured surface and you want to carry it to the top of the implant. If you have very porous bone and you want to use an implant surface that will improve your chances of success, HA coating should be considered, although not necessary with the soft bone surgical protocol incorporated into the legacy and screw vent implant systems. About a decade ago, Nobel's one-piece Nobel Direct implant was sold with the porous TiUnite surface extending up the neck into the soft tissue area. Nobel claimed this promoted, quote, soft tissue integration, end of quote. That implant was eventually taken off the market after a class action lawsuit was filed by a dentist who had multiple failures with this implant. Apparently, Nobel's answer now is to create a smooth surface on the top few millimeters of the implant by anodizing, while claiming that this creates muco-integration. The grooves at the top of the Nobel Active are there because that area is intended to be, and hopefully remain, subcrestal. Anodizing the neck makes it smoother than just leaving it as a machine surface, and we know that the Branemark machine surface implant often experience bone loss to the first thread. The only rationale to color the neck gold would be if resorption took place, exposing it to the soft tissue, and then only in the aesthetic zone. From the reference to, quote, muco-integration, end of quote, it sounds like Nobel anticipates bone loss from this implant, resulting in the gold neck being exposed to the soft tissue. Certainly, there is no rationale for a gold-colored neck in the posterior, and especially not on an all-on-4 case as shown here. These studies from the late 1980s, comparing all four surfaces used by Corvent, shows that by 2 months, HA-coated screw vent implants doubled the attachment strength as measured by torque removal. By the early 1990s, SBM replaced acid etch and TPS surfaces on Corvent implants. The same SBM surface is being used today by Implant Direct, BioHorizons, and Zimmer Biomet. Zimmer Biomet is promoting the trabecular metal surface screw vent as a premium price with a trabecular metal insert in its midsection. This eliminates about 2/3 of the thread engagement and provides a porous surface that could become a hygiene problem if exposed from bone loss. Initially, Zimmer had an FDA recall on this implant, requiring that it change the surgical protocol in dense bone to eliminate thread engagement by the apical threads of the implant. When the apical threads engaged bone, the threaded part below the trabecular metal was separating from the implant. The reason was that they slipped this trabecular metal on the implant core and then weld the bottom threaded portion. Using step drills, this apical threaded portion would engage dense bone and break off as the implant continued to be turned. From this X-ray, it appears that the implant has been changed from tapered to straight, giving up on the advantages of bone compression from inserting a tapered implant into an undersized socket. Straumann claims that delivering its implant in a vial filled with sterile saline will make the surface more hydrophilic and that this will reduce healing time. The question is whether there is any clinical advantage to this packaging variation that can justify the extra $67 Straumann charges in the US. Straumann relies on studies showing that SL-active implants were successful when loaded at 4 weeks, but these studies did not use a control of the same implant loaded immediately, which also may have shown high success. Another unique selling proposition of Straumann implants is its use of titanium zirconium alloy called rock solid rather than titanium 6Al4V alloy used by most other implant companies and the orthopedic industry. Titanium zirconium alloys are more brittle and therefore potentially more likely to fracture. This Boozer study in mini pigs comparing SLA to SL-active surfaces on Straumann implants shows that torque removal during the 3rd to 4th week following implantation of an SL-active implant did not dip as much as the SLA surface implants. Both initially and by the 8th week, there was no difference in torque removal. This chart from a Zimmer dental study compared primary stability achieved with its tapered screw vent implant to that of the Nobel Active, Nobel Replace, and Straumann straight bone level implants. It generated 100% more than Straumann's implant. From a clinical standpoint, achieving high initial torque allows for immediate loading of the implant. What the torque values are at the 3rd to 4th week after implantation is of little consequence. You're either going to get enough initial torque to load the implant immediately, or you're going to leave it for 8 to 12 weeks and let healing occur before placing the implant into function. Far more important is the relationship between the implant design and its surgical protocol in achieving high initial stability to allow immediate loading even in soft bone. These pictures show blood running up SBM and HA-coated Implant Direct implants, so claims of unique advantages by Straumann of its hydrophilic implant surface have never been clinically proven. This slide demonstrates the disadvantages of subcrestal placement of implants. While this can be done with any two-piece implant, the Morse taper connection of the ankylose and bicon implants often requires subcrestal placement in order to drop the height of contour of the abutment below the soft tissue for aesthetics. This is because their friction-fit abutments emerge from the implant as a narrow post and require several millimeters of length to create an acceptable emergence profile. Subcrestal placement sacrifices at least 2 millimeters of crestal bone support and creates an infrabony defect. I've simulated graphically what a more natural emergence profile would look like if an implant with a screw-retained abutment was placed level with the crest of the ridge. This bicon implant was placed about 3 millimeters below the crest of the bone. With this type of placement, a contouring drill is often needed to remove crestal bone in order to seat the abutment. The case on the right, using a Legacy 4 implant placed subcrestal, shows that the use of an older healing collar without a concave neck failed to fully seat. It was replaced with the healing collar provided free with the implant. A recent study by Selena et al. In the International Journal of Oral Implantology, 2019, Volume 12, confirmed that placing an implant 1.5 millimeters subcrestal compared to only 0.5 millimeters demonstrated no improvement in aesthetics or clinical difference in bone loss. Doing so can obviously complicate attachment of healing collars and abutments. Platform switching describes the use of an abutment of smaller diameter than that of the implant platform to medialize the implant abutment margin, a design that some claim reduces bone loss. Such a ledge is inherent with internal connection implants having a lead-in bevel because of the wall thickness needed to support the abutment. This randomized clinical trial concluded that, quote, it could not confirm the hypothesis of a reduced peri-implant bone loss at implants restored according to the concept of platform switching, end of quote. This slide shows the use of length-specific tapered drills with the Neodent and Nobel Replace system of tapered implants. This requires that the final sizing drill need to be both length-specific and diameter-specific for each implant, adding significantly to the number of drills. The use of straight step drills with score lines and increasing the diameter of the drills depending on the density of the bone reduces the number of drills needed to insert a tapered implant, such as the screw vent and legacy implants. In very dense bone, a crestal bone drill is used to open the top of the socket to match the diameter of the implant neck. Using step drills with score lines for insertion of tapered implants dramatically reduces the number of drills needed. Many screw implant systems, whether tapered or straight, include bone taps for creating threads in dense bone. Implant Direct does not need to make bone taps for its tapered implants for several reasons, including the strength of its internal hex connection, the efficiency of its self-tapping grooves, and its surgical drill protocol. In very dense bone, the final sizing drill is just slightly smaller than the diameter of the implant, and crestal bone drills are provided to enlarge the top of the socket to match the diameter of the neck of the implant in very dense bone. This slide shows a fractured Nobel Replace implant being removed and the warning label on the Nobel Replace implant vial not to exceed 45 Newton centimeters of torque during insertion. This is due in part to the wall thickness and in part to the use of commercially pure titanium rather than titanium alloy used by most other implant manufacturers. This is because Nobel's Ti-Unite surface, created by anodizing, apparently will not form on an alloy surface. This Nobel ad shows a bird nestled in an exhaust pipe to make the point that just because something fits doesn't mean it works. The ad also shows an SCM of a fractured Nobel active implant and implies that the fracture was caused by the use of mismatched competitors' abutments. Implant Direct received FDA marketing approval to claim compatibility of its RePlant and interactive abutments by demonstrating that it had accurately reverse engineered the internal connection of the Nobel Replace and Nobel Active implants. Certainly, After Danaher acquired 100% of Nobel and Implant Direct, and Implant Direct is under the management of Nobel executives, Nobel could share engineering drawings to confirm the compatibility if it had any real concerns. Instead, Nobel's management has deleted any Implant Direct marketing materials, catalogs, and videos referencing prosthetic compatibility with Nobel implants in order to preserve sales of its more expensive Nobel abutments. Both Straumann and Nobel advise against the use of aftermarket compatible abutments with their implants. Yet Straumann acquired Medentika and sells abutments for its competitors' implants, and Nobel sells CAD milled abutments for its competitors' implants. In conclusion, from 1982 to 2017, I've been issued 33 U.S. patents related to dental implants. Just a couple of sayings that relate to the process of inventing new products. Discovery consists of seeing what everybody has seen and thinking what nobody has thought. Also, the greatest obstacle to discovery is not ignorance, it is the illusion of knowledge. When you think you know it all, you just stick with what you know. Thank you very much.